Have you ever noticed those like really intricate patterns you find out in nature?
Yeah.
Yeah, like the way sunflower seeds spiral out from the center or the
Mm.
perfect little hexagons in a honeycomb. It's kind of mind-blowing when you stop and think about it.
It really is. There's so much beauty and order in the natural world.
Right, and it makes you wonder if there's like some kind of secret mathematical code underlying it all.
Absolutely. There's a deep connection between math and nature.
So today we're going to take a deep dive into the fascinating world of patterns, specifically a type of numerical pattern called arithmetic progressions.
Oh, cool. I love patterns. They're everywhere once you start looking for them.
Yeah,
Yeah.
and they're not just in nature. You see them in everyday life too.
Oh, totally.
Like imagine someone named Marina. She starts a new job making 8,000 euro a month,
Okay.
and every year she gets a raise of 500 a year.
Sounds like a good deal.
Yeah, so her salary goes up in a predictable way.
Makes sense.
8,000, then 8,500, then 9,000, and so on.
A steady climb.
Yeah, exactly. It's like climbing a ladder,
Okay.
where each rung is a little bit shorter than the one below it.
Okay, I can see that.
See, the bottom rung is 45 centimeters, and each one above it is 2 centimeters shorter.
So 45, 43, 41, and so on.
Exactly. You can picture that gradual decrease in length.
Mm-hmm.
Now, sometimes things change at a faster pace.
Okay.
Think about a savings scheme where your money grows by 25% every 3 years.
Right.
If you invest 8,000 euros, after 3 years, you'll have 10,000.
Okay.
Then 12 euro 500, then 4 1/3 625 save. It's accelerating.
Right. That's a different kind of pattern.
Yeah, it's not just a constant amount being added each time.
Definitely not.
And then there was those really simple patterns, like the number of squares in bigger and bigger squares.
Yeah.
A 1 by 1 square has 1, a 2 by 2 has 4, a 3 by 3 has 9, and so on.
That's the sequence of square numbers.
Right, 1, 4, 9, 16.
Each term is the previous term squared.
Okay, let's bring it back to something a little more relatable.
Sure.
Imagine Shaquila. She puts $100 in her daughter's piggy bank on her first birthday.
All right.
And every year she adds 50 more than the previous year.
So 150, 200.
Exactly. A steady increase in savings over time.
I like that one.
And of course, there's that classic pattern, the Fibonacci sequence.
Oh, yeah, the famous rabbit problem.
Right. 1, 1, 2, 3, 5, 8. You get the next number by adding the previous 2.
It pops up in the most unexpected places.
It really does. But today we're focusing on a specific type of pattern called arithmetic progressions, or APs.
Got it. So what makes an arithmetic progression special?
Well, in AP, each term is obtained by adding a fixed number to the previous term.
Oh, okay, so it's all about that constant difference.
Exactly. And we call that fixed number the common difference.
So it's like those examples we talked about, Rena's salary, the ladder rungs.
Exactly. In Rina's case, the common difference was 500. For the latter, it was minus 2 centimeters.
Right, because the rungs were getting shorter.
And that common difference can be any number, positive, negative, or even 0.
I guess if the common difference is 0, all the terms would be the same.
You got it. It would be a very simple AP, but still an AP.
Okay, that makes sense.
Now, mathematicians like to use shorthand, so they have symbols for all these things.
Oh, of course. They love their symbols.
We represent the first term with A, or sometimes a euro if we want to be really specific.
Okay.
The second term is air. The nth term is A0Y E20 by 820 by 99, and the common difference is D.
Got it. So the key relationship is that the difference between any two consecutive terms is always D?
Precisely. So A euro is D, and A euro is also D, and so on.
I see. It's all about that constant difference.
Now let's look at some real-world examples where APs pop up.
Okay, sounds good.
Imagine a line of students where each student is 1 centimeter taller than the one in front of them.
Right.
Maybe the first student is 147 centimeters, then 148, then 149, all the way up to 157.
Got it. So the heights form an AP with a common difference of 1.
Right. And it's a finite AP because it has a last term.
Okay.
What about the minimum temperature recorded each day in January?
All right.
Let's say it starts at minus 3.1 degrees Celsius.
Yeah.
And increases by 0.1 degrees each day.
So negative 2.1, negative 2.9, and so on.
Yeah, up to minus 2.5.
Another finite AP this time with a common difference of 0.1.
Right, and that common difference can be negative too.
Oh, right, like those shrinking ladder rungs.
Exactly. Or think about paying off a loan with fixed monthly installments.
Okay.
Maybe you start with 0,000 and pay 50 each month.
So 900, 850 down to 50.
You got it. A finite AP with a common difference of negative 50.
Negative because the loan balance is decreasing.
Right. Now, what about something like cash prizes for the top student in each grade?
Interesting.
Maybe 200 for grade, €1 250 for grade 2, or 300 for grade 3, all the way up to 750 for grade 12.
Okay, so the prizes form a finite AP with a common difference of 50.
Exactly. And one more edge, you save 50 every month.
Right.
So at the end of month 1, You have 50-month, 200-month, 3 or 150, and so on.
Got it. Another AP with a positive common difference.
Exactly. So you see, APs can represent all sorts of real-world scenarios.
Yeah, I'm starting to see the pattern.
Now, let's generalize this a bit. The general form of an AP is a plus D, a plus 2D, plus third, and so on.
Okay, so the first term is A, and then we keep adding the common difference D.
Exactly. And remember, we talked about finite and infinite APs.
Right, the finite ones have a last term, while the infinite ones go on forever.
Like the natural numbers 1, 2, 3, 4. That's an infinite AP with a common difference of 1.
Cool. So to define an AP, we need two pieces of information the first term and the common difference.
You got it. Let's try a few. If A is 6 and D is 3, what's the AP?
6, 9, 12, 15.
Right, now what if A is still 6, but D is now been 3?
6, 3, R6, Mecca 3.
Good. Let's do a couple more. What if A is magnitude 7 and D is magnitude 2?
Mat of a 7, 9, 11, 13, and so on.
Excellent. Now try A equals 1.0 and D equals 0.1.
Okay, 1.1, 1.2, 1.3.
Perfect. Now what if A is 0 and D is 12?
That would just be 2, 2, 2, 2.
Exactly. All the terms are the same,
Yeah.
but it still fits the definition of an AP.
Okay, I get it.
How do we know if a list of numbers is actually an AP?
We need to check if the difference between any two consecutive terms is the same.
Precisely. Well, look at the sequence. 6, 9, 12, 15, 9 minus 6 is 3, 12 minus 9 is 3, 15 minus 12 is 3. It's consistent.
So it's an AP with a common difference of 3.
Now, what about 6303?
3 minus 6 is minus 3, minus 3 is minus 3, no 3, minus 0 is minus 3. It's also an AP, but with a negative common difference.
Exactly. But if we take a sequence like 1, 1, 2, 3, 5.
1 minus 1 is 0, but 2 minus 1 is 1. That difference isn't constant.
Right, so that's not an AP.
Okay, I think I'm getting a feel for this.
Good. Now remember the formula for finding the common difference, D. It's D equals A0 by 3 by A20 by 99 euros minus A0 by 20 by A20 by 99.
Right. You take any term and subtract the term right before it.
Exactly. Let's do a quick example. The sequence is 32, 12, 12, 32. What's the first term and the common difference?
As the first term, A is 32.
Right. Now the common difference.
Well, 12 minus 32 is minus 1, so D is minus 1.
You got it. Okay, let's try something a little more challenging.
Bring it on.
I'll give you some sequences, and you tell me if they're APs. And if they are, what are the next two terms?
All right, I'm ready.
First one, 4, 10, 16, 22.
Oh, okay, 10 minus 4 is 6, 16 minus 10 is 6, 22 minus 16 is 6. Yep, it's an AP with a common difference of 6. The next two terms would be 28 and 34.
Excellent. Next one, 1, 1, 1, there, 3.
Minus 1 is 9 is 2, then it's a 3. Minus 1 is 9 is 2, then a 5. Minus 3 is 9 is 2. Another AP common difference is 9 is 2. The next two are 9 is to 7 and 9 is 9.
Perfect. Next one, 9 is 2, 2, 9 is 2, 9 is 2.
2 minus 2 is 4, but minus 2 is 9 is 4. Nope, the difference isn't constant. That's not an AP.
Right. Last one, 1, 1, 1, 2, 2, 2, 2, 3, 3.
1 minus 1 is 0, but 2 minus 1 is 1. Not an AP.
So you're a pro at identifying APs now.
I think so.
Now let's talk about finding a specific term in an AP, like say the 100th term.
We wouldn't want to calculate all the terms before.
Exactly. Remember Rena's salary?
Yeah.
We could figure out her salary in the 3rd, 4th, or 5th year by just adding 500 repeatedly.
Right, but that would get tedious for a larger number.
Exactly. So there's a formula for that. The nth term of an AP denoted by A0 x E20 by A20 by 99 equals A plus N minus 1 times D.
Okay, so we take the first term A and add the common difference D a certain number of times.
Exactly. And the number of times we add D is N minus 1 because we've already accounted for the first term.
That makes sense.
If the AP has a total of M terms, then the last term is represented by A0 x E by A20 by 98, which is sometimes also called L.
So we can use this formula to jump directly to any term without calculating all the ones before it.
Precisely. Let's try an example. Find the 10th term of the AP 2712.
Okay, so A is 2, D is 5, and N is 10.
Right. Plugging those into the formula, we get A0 equals 2 plus 10 minus 1 times 5.
So 2 plus 9 times 5, which is 47.
Exactly. The 10th term is 47.
Cool.
Okay, another one. Which term of the AP 21, 18, 15 is equal to 88, 81?
So A is 21, D is 9 is 3, because the terms are decreasing, and we want to find N when 88, 20 by 8, 20 by 99 is 9 is 81.
Exactly. Let's plug those values into our formula.
Okay, so 9 is 81 equals 21 plus N minus 1 times 9 is 3.
Good. Now we just need to solve for N.
All right, let's simplify that. We get Madish 81 equals 21 minus 3N plus 3.
Right, which becomes Manish 81 equals 24 minus 3N.
So 3N equals 105, and therefore N is 35.
Exactly. So the 35th term of this AP is Nadish 81. Now a follow-up question. Is there any term in this sequence that's equal to 0?
Okay, so we need to find N when A0 at E20 by A20 by 99 is 0.
Right, let's plug in the values and see what we get.
0 equals 21 plus N minus 1 times minus 3.
Good. Now simplify that.
0 equals 21 minus 3n plus 3.
All right, keep going.
So 0 equals 24 minus 3n, which means 3n equals 24, and n is 8.
You nailed it. So the 8th term of this AP is 0.
Cool.
Now let's try a different kind of problem. We know that the 3rd term of an AP is 5 and the 7th term is 9. Can we figure out the entire AP?
That's interesting. We only have information about 2 terms.
Right. But we can use our nth term formula to set up a system of equations.
Okay, I see how we can do that.
We know A, which is the 3rd term, is a plus second, and that equals 5.
And a, which is the 7th term, is a plus 6p, and that equals 9.
Exactly. Now we have 2 equations and 2 unknowns, A and D. We can solve for them.
All right, let's subtract the first equation from the second to eliminate a.
Good. What do you get?
4d equals 4, which means d must be 1.
Perfect. Now substitute that back into either equation to find a...
Okay, I'll use the first one. A plus 2 times 1 equals 5.
Right, solve for us out.
So a plus 2 equals 5, which means a is 3.
You got it. So the AP is 3, 4, 5, 6, 7.
We figured out the entire sequence just from knowing 2 terms.
That's the power of the nth term formula?
It's like a mathematical detective tool.
Okay, one more challenge. Is the number 301 a term in the sequence 5, 11, 17, 23?
Okay, first we need to check if it's an AP.
Right. What do you think?
11 minus 5 is 6, 17 minus 11 is 6, 23 minus 17 is 6. Yep, it's an AP with A equals 5 and D equals 6.
Good. Now, how do we see if 301 is a term?
We can set A0 by E20 by 820 by 99 equal to 301 and solve for n. If n is a whole number, then 301 is a term.
Exactly. Go for it.
All right, so 301 equals 5 plus n minus 1 times 6.
Right. Come on.
301 equals 5 plus 6n minus 1, which means 6n equals 302.
Keeping.
And n equals 302 divided by 6, which is about 50.33.
So what does that tell us?
Well, n has to be a whole number to represent a position in the sequence.
Right,
Since
but-
we got a fraction, 301 is not a term in this AP.
Okay, good. Now let's switch gears a bit and talk about finding the number of terms in an AP.
Okay, sounds interesting.
How many 2-digit numbers are there that are divisible by 3?
Well, the smallest one is 12, then 15, 18, up to 99.
And that forms an AP, right?
Yes, with a common difference of 3.
Exactly. So A is 12, A0 by E20 by 820 by 99 is 99, and we want to find n.
All right, we can use the nth term formula again.
Go ahead.
99 equals 12 plus n minus 1 times 3.
Right.
Simplifying that, we get 99 equals 12 plus 3n minus 3.
Yeah.
So 99 equals 9 plus 3n, which means 90 equals 3n and n equals 30.
Excellent. So there are 32-digit numbers divisible by 3.
Makes sense.
Now let's try something a bit more tricky.
Okay, I'm intrigued.
Find the 11th term from the end of the AP 1074 all the way to number 62.
So we need to work backwards.
Kind of. But first we need to know how many terms there are in total.
Right, we can use the formula L equals A plus n minus 1 times D to find n.
Exactly. We know A is 10, D is minus 3, and L is minus 3 and 3.
So 9 is 62 equals 10 plus n minus 1 times minus 3.
Right. Simplify that.
9 is 62 equals 10 minus 3n plus 3.
Keep going.
So natix 62 equals 13 minus 3n, which means 3n equals 75 and n is 25.
Excellent. So there are 25 terms. Now how do we find the 11th term from the end?
Well, the 11th term from the end is the same as the 15th term from the beginning.
How did you get that?
If there are 25 terms total and we count 11 back from the end, we land on the 15th term.
You're right. So we need to find it.
Using the nth term formula, AOR equals 10 plus 15 minus 1 times minus 3.
Good.
Which is 10 plus 14 times minus 3, or 10 minus 42, which is minus 32.
Exactly. So the 11th term from the end is minus to 2.
Got it.
Now there's a clever trick we could have used.
Oh, what's that?
We could have reversed the AP, making natix 62 the first term and 3 the common difference.
Interesting.
Then the 11th term from the beginning of this reversed AP would be the same as the 11th term from the end of the original AP.
That's pretty slick. Let's check it.
Okay.
So a euro of the reversed AP would be natix 62 plus 11 minus 1 times 3,
Right.
which is natix 62 plus 10 times 3, or natix 62 plus 30, which is natix 32.
The same answer.
It works.
Let's move on to a financial example.
Okay, money time.
If you invest 8,000 euro at a simple interest rate of 8% per year,
Right.
the interest you earn each year forms an AP.
Really? How so?
Well, the first year you earn 80, the second year 160, the third year 240, and so on.
Ah, I see. The interest increases by 80 each year.
Exactly. So A is 80 and D is also 80. Now, what's the total interest earned after 30 years?
That would be the 30th term of the AP,
Right. So 80 equals 80 plus 30 minus 1 times 80.
which is 80 plus 29 times 80, or 80 times 30, which is 2,400.
Exactly. So after 30 years, you'd have earned 2,400 in simple interest.
Simple interest is a straightforward example of an AP.
It is. Now, let's consider a situation involving rows of plants.
Okay.
In a flower bed, there are 23 rose plants in the first row, 21 in the second, 19 in the third, and so on, until there are only 5 in the last row.
Right.
How many rows are there in total?
So the number of plants in each row forms an AP 23, 21, 19 down to 5.
Right, with A equals 23, D equals minus 2, and A0 back E20 by A20 by 99 equals 5. We want to find N.
I can use the nth term formula 5 equals 23 plus n minus 1 times 2.
Good, simplify that.
5 equals 23 minus 2n plus 2.
Right.
5 equals 25 minus 2n. So 2n equals 20 and n is 10.
Excellent. So there are 10 rows of rose plants.
Okay, I think I'm getting the hang of these AP problems.
You're doing great. Now let's talk about finding the sum of a certain number of terms in an AP.
Okay, that sounds like it could get complicated.
It can be, but luckily there's a formula for that too.
There always seems to be a formula.
Math is all about patterns and formulas. Remember Shaquila and her daughter's piggy bank?
Yeah, she added a different amount each year.
Right, we wanted to know the total amount saved after 21 years.
Adding up all those numbers manually would be tedious.
Exactly. So we need a formula for the sum of the first n terms of an AP.
Makes sense.
And there's a cool story about a famous mathematician named Gauss who figured out a shortcut for this kind of problem when he was just a kid.
Oh, I've heard about this. He was a genius.
He was. His teacher asked him to add up all the numbers from 1 to 100.
Wow.
Gauss realized that if you pair the first and last numbers 1 and 100, then the second to last numbers 2 and 99 and so on, each pair adds up to 101.
Oh, I see that.
And since there are 50 pairs, the total sum is just 50 times 101, which is 50/50.
That's brilliant.
It is. And we can use a similar idea to derive the formula for the sum of an AP.
Show me.
Let S represent the sum of the first n terms. So S equals A plus D plus A plus 2D, all the way up to a plus n minus 1 times D.
Okay, that's the sum written out the usual way.
Now let's write the same sum, but in reverse order.
So S also equals A plus n minus 1 times D plus A plus n minus 2 times D down to A.
Exactly. Now if we add these two equations together, term by term, something interesting happens.
What's that?
The first terms add up to 2A plus n minus 1 times D.
Okay.
The second terms also add up to 2A plus n minus 1 times D.
A so on for all the terms.
Right, so we end up with 2S equals n times 2A plus n minus 1 times D.
Got it. Now we just need to solve for S.
Exactly. We divide both sides by 2, and we get the formula S equals n2 times 2A plus n minus 1 times D.
That's the formula for the sum of an AP.
And there's another way to write it. If we substitute A0xZ20 by A20 by 99, which is a plus n minus 1 times D for the last term, we get S equals n2 times A plus A0A20 by A20 by 99.
Okay, so we can use this formula if we know the first and last terms.
Exactly. And it simplifies even further. If we use L to represent the last term, then S equals N2 times A plus L.
So we have two formulas for the sum depending on what information we have.
Exactly. Let's revisit Shaquila's piggy bank. We had A equals 100, D equals 50, and N equals 21.
Okay.
Plugging those values into the first sum formula, we get S0 equals 212 times 2 times 100 plus 21 minus 1 times 50.
Simplifying that, we get 10.5 times 200 plus 20 times 50.
Right, which is 10.5 times 1200 or 12 and 600.
So the total saved after 21 years is 12,600.
Exactly. Now there's a neat little connection between the sum of the first n terms, A0x E20 by A20 by 99, and the nth term, A0 guy A20 by A20 by 99.
What's that?
The m term is equal to the sum of the first n terms minus the sum of the first n minus 1 terms.
So A0x E20 by A20 by 99 equals S0 x E20 by A20 by 99 minus S0 x E20 by A20 by 99 euro.
Precisely. It's like if you add up all the terms up to n and then subtract the sum of all the terms before n, you're left with just the nth term itself.
That's a cool relationship.
It is.
Yeah.
Well, let's do some examples.
Fire away.
Find the sum of the first 22 terms of the AP 8, 3 to 2.
Okay, so A is 8, D is -5, and N is 22.
Right. Using our sum formula, we get S0 equals 222 times 2 times 8 plus 22 minus 1 times -5.
Simplifying that, we get 11 times 16 plus 21 times -5.
Which is?
11 times negant 89, or nect is 979.
Exactly. So the sum of the first 22 terms is -9.
Negative because the terms are decreasing.
Okay, now, little twist. What if the sum of the first 14 terms of an AP is 1050 and the first term is 10? Can we find the 20th term?
So we know S0 is 1050, N is 14, and Its0 is 10.
Right. We can use the sum formula to find D.
Okay, so 1050 equals 142 times 2 times 10 plus 14 minus 1 times D.
Good. Now solve for D.
Simplifying, we get Haskell 50 equals 7 times 20 plus 13.
Right.
Dividing by 7, we get 150 equals 20 plus 13.
Keep going.
So 130 equals 13, and D equals 10.
Now that we know A and D, we can find the 20th term.
All right. A row equals 10 plus 20 minus 1 times 10.
Great.
Which is 10 plus 19 times 10, or 10 plus 190, which is 200.
So the 20th term is 200.
Got it.
Now for another challenge. How many terms of the AP 24, 21, 18 must we take so that their sum is 78?
Okay, so A's 24D is -3, and we want 0xe20 by 820 by 99 to be 78. We need to find n.
Exactly.
Using the sum formula, 78 equals n2 times 2 times 24 plus n minus 1 times the ninth 3.
Okay.
Simplifying, we get 78 equals n2 times 48 minus 3n plus 3.
Yeah.
70 equals n2 times 51 minus 3n. Multiplying both sides by 2, we get 156 equals n times 51 minus 3n.
Right.
Expanding that, we get 156 equals 51 minus 3n on my 3.
Okay, so 3n minus 51n plus 156 equals 0.
And we can simplify that by dividing by 3.
Right, n minus 17 plus 52 equals 0.
Now we need to factor that quadratic.
Okay, I think it factors as n minus 4 times n minus 13 equals 0.
Excellent. So what are the possible values of n?
4, 13.
And why do we get 2 answers?
Because the terms are decreasing.
Yeah.
After the fourth term, the terms become negative.
Right. And it turns out that the sum of the terms from the 5th to the 13th is 0.
So whether you take the first 4 terms,